I'm going to talk about the Go programming language, which is going to be, we hope, going open source on November 10th, which is in just a couple of weeks. This talk is a little bit before then, so there's some future tense for things like links and so on, but everything should be as reported by the time we actually go public with this stuff. You can see we have a website we're setting up, which will be the public domain, public viewable domain for that. So what is it? Well, I'm going to talk about all these pieces, but it is new, experimental, concurrent, garbage-collected systems language. Experimental because we don't believe this is the answer to everything, but we're playing and we think it's gotten to the point where it's time we should probably tell the world about it. It's concurrent because it's really important in the modern world. It's garbage collected because we have an opinion on that stuff, which I'll talk about quite a bit later. And it's a systems language in the sense that we intend it to be written, to be used to write things like web servers and other system aspects like that. You have more control over some things than you have in other languages like, say, Java or Python. But it works like a systems language when you use it. On the other hand, it's very good at things we found for things like front ends or just general programming. So although it's designed as a systems language, it has much broader use than just that. Can't give a talk without showing you Hello World. There's Hello World with the world being Japanese, which I won't attempt to pronounce. But you can see that it looks vaguely C-like, although there's some weirdnesses about it, and we'll talk about what those weirdnesses are. Who's involved? Well, I'm giving the talk, but it's by no means my project. There's a bunch of people involved, and I want to make sure everyone's clear that some of the names are really important here. Robert Griesmer, Ken Thompson, and I started talking about doing something to solve the problems we were seeing with other environments sometime around 2 years ago, in late 2007. We played mostly at the whiteboard for a few months, figured some things out. But by middle of 2008, we had a toy compiler, and things were starting to look interesting. And we started working on the stuff for real. And around that time, Ian Taylor joined and Russ Cox joined, and the 5 of us did most of the work, but we've had a lot of help from a lot of people that this slide is too small to name. So I want to make it clear this is a collaborative effort, and the collaboration is growing. Why? Well, the reason is things were just taking too long to compile, too long to build, too long to think about. We want to program fast, and we want to program fun. And to make programming fun, you have to find ways to speed things up and make things work better. Not just the code itself, but the process of writing the code needs to be efficient. So what's happened? Programming used to be fun. What went wrong? Well, it's interesting. There's really been no new major systems language in at least 10 years, arguably longer. But in that decade, a lot has changed. The libraries have gotten bigger. Professional programming has, to a large extent, become a layering process. And so we layer more and more stuff on, and we also broaden out the base. The libraries get really big. There's lots of them. They communicate with dependencies to one another. And so the forest has become a thicket, and it's sometimes kind of hard to cut your way through it. Networking has pretty much taken over the world as the way to think about computing. The old Sun thing about the network is the computer is pretty much true today, but the languages don't really reflect that. There's a lot of client-server kind of stuff, especially in the system space. Languages don't really help you there too directly. Of course, we're talking about massive compute clusters now, and again, the languages are designed for single processors. They don't really work very well in that model. And on a related note, multi-core CPUs are taking over too. It's getting harder to buy a high-end computer with only one processor in it. They tend to be multi-core, sometimes multi-chip multi-core. And again, the languages that we're using weren't really designed with that kind of stuff in mind. And it's also gotten, I think this is the thing that finally pushed us to try to do something, it's just gotten too slow to build software. The tools are slow. They have a hard problem to do, but they tend to be slow, and they're getting slower. The computers have sped up enormously, but the software development process, if anything, has gotten slower over the last 10 years. The dependencies are uncontrolled, and the languages don't help you control them, so you tend to spend a lot of time maybe building things you don't even need, but you don't know it, can't prove it. The machines have also stopped getting faster. They've gotten more, but they haven't gotten faster. There are more processors, there are more of them, but the actual clock speed has hardly changed in the last few years. And Moore's law, to some extent, is petering out. And yet the software gets bigger and bigger and bigger. And so somehow it feels like if we don't do something, then software construction is just going to become unbearably slow. And we need to think about the process of making it fast again. Robert Griesemer observes that a lot of the interesting work in languages in the last few years has been because a lot of the people using these standard systems languages like C, C++, even Java, are finding the type systems are very sort of clumsy. They're hard to work with. And if they move to the dynamic languages, the Pythons, the Rubys, even the JavaScripts of the world, they have a lot more fun because the type systems don't get in the way so much, at least as long as the program keeps running. And so the challenge here is to try to deal with this. You want typing, you want good typing because it makes programs robust, but it can be done badly. And we argue that in some ways, if not done badly, it should at least be done a different way. Sometimes good ideas, in principle, make bad practice. And a good example of that is the const keyword in C and in C++, which was very well intentioned and seemed to address a real need in making programs safer. But it tends to make programming awkward in a lot of ways that sort of isn't worth the benefit you get back from using it. Also, there's this notion of everything being a type hierarchy in object-oriented programming. And yet, the types in large programs don't really naturally fall into hierarchies. We find a way to make them fit, but it's a bit of a struggle. And programmers spend too much time refactoring their code, juggling type trees around. And that has very little to do with the implementation and a lot to do with the way the language is forcing you to think. We'd like to sort of step back from that model. And in short, therefore, with the way type systems work today, you can be productive or you can be safe, but you can't really be both. And that seems like a shame. We should be able to fix that. So why a new language? Why don't we just fix what we've got? Well, some of the problems are just fundamental to the way the languages are thinking, the way the type systems work, the way they're compiled, the way dependencies are managed. The languages themselves have these problems endemic in them. And to fix them, you have to rethink the language as itself. For instance, the libraries can't help you because adding anything to try to fix some of these problems is going in the wrong direction. There's too much already. We need to trim down, cut the fat, make things cleaner. Fixing it by adding software isn't going to do it. You have to sort of step aside and do something separate. And so we decided, Robert, Ken, and I, a couple of years ago, that we need to start over. Just take a step away and think about the way programs are written and constructed and try to make a language that makes that process a lot easier. So it's a new language. What are the goals of this language? The sort of short version of the story is we want the efficiency of a statically compiled language, that means truly compiled language, but the ease of programming of a dynamic language. And I think we've come pretty close to achieving that. You can decide for yourself as we go on. Safety is critical. It's critical that the language be type safe and that it be memory safe. It's important that a program not be able to derive a bad address and just use it, that a program that compiles is type safe and memory safe. That's a critical part of making robust software. And that's just fundamental. We want good support for concurrency. I'll talk a little bit about that. Communication, talk about that too. Those are tools that can help you build software that runs in the network or on multi-core CPUs. We want to a garbage collected thing because a lot of the bookkeeping that goes on inside modern programming, especially in C and C++, has to do with memory management. And that can be totally automated. And we believe is the word, that you can do that efficiently and essentially latency free, that the garbage collecting technology is advanced to the point where a garbage collected systems language actually makes a lot of sense. And so we'd like to do that. And also, we'd like the compilers to just run fast. Everyone knows this slide. And there's some truth to it. You spend too much time waiting for compiles. So let me give you a compilation demo here. This is a, how do we do this here? This is a directory of Go code. If you look in here, there's about 1,300 lines. So I'll make clean, and then I'll just do make here. There, I just built the math library. That's compiled. It's efficient code. Clean again. In case you wonder if I can type. Okay, time make. Okay, so that's about pretty accurately, 200 milliseconds real time to build a library. That feels about right. For the last year or so, those of us working with Go have been getting used to 100 millisecond builds on one machine. That's running on my laptop, by the way. That's not some distributed thing. That's one processor, one build. And just to prove it a little better, let me make clean. This is the complete Go source tree. All of the libraries written in Go. It's something of order, I think it's about 120, 130,000 lines. So included in here are regular expressions, flags, concurrency primitives, the runtime, the garbage collector, pieces. Oh, it's finished. Okay, so that was one processor. I could have parallelized it a bit better. But that's 8 seconds. That feels long to me now. That's a long time because this is all the software that's there, and 8 seconds is a long time, but you're getting a lot done in that much time. Just to remind you, let me go back here. That's what you want to see. You want to have carriage return time for your compilations, and you can be done. So let me get that set for later, and we'll go back to this. Okay, so we think we've got fast compilation, and I can't tell you what a difference that makes to your life. Sometimes hours and hours go by when people finally show up at my office and say, hey, you didn't answer my mail. I've been looking at my mail. I've actually been getting work done. Okay. So to do this language, we had to have some principles on which it's built. And there are actually some fundamental principles in here that in some ways I think differ from some of the other languages that are out there. So I'd like to go through them. One of them is that we tried as much as possible to keep the concepts orthogonal. For instance, in the interface stuff, which I'll talk about, the concept of implementation versus interface are completely orthogonal. They're separate things. They don't interact. And you don't define them together. You define them as separate objects, and that makes a lot of stuff cleaner. And in practice, this is because a few orthogonal features that cover the space work a lot better in practice than a lot of overlapping ones. That's a principle that's a little vague, but I think you know what I'm getting at. The grammar is very regular and very simple. It's actually conflict-free and can be parsed without a symbol table. There's no conflicts in it. That makes it easy to write tools like IDEs or editor plugins, things like that, debuggers, because the parsing the language and understanding it in a program is actually pretty straightforward. We tried to reduce the typing. What I mean by that is that we want the language to work things out. You tend to type too much when you're programming in modern object-oriented languages. You tend to write statements like that. That's literal. If you change foo for a much longer word, that's an example I found in some code I won't name. And I just, foo should just go away. You shouldn't have to type all those foos. That's crazy. So you want to get rid of the bookkeeping. You want the type system to automatically work stuff out, but you still want it to be safe. You want to be type safe, but well handled. And also, not only do you want to reduce typing, you want to reduce typing. You want the types to sort of melt away into the background. You want it to be clear. You don't want a type hierarchy. At least we don't want a type hierarchy. And I'll show you some examples of why that actually helps. We just think that programming by constructing type hierarchies is not the way to go. We have an alternate world. However, Go is a profoundly object-oriented language, arguably more object-oriented than, say, Java or C++. And I'll show you why. So the big picture, there's some fundamentals. We have a clean, concise syntax. We have a very lightweight type system. We got rid of implicit conversions because although they're convenient, they tend to cause a lot of confusion, particularly in the old C rules for things like the usual conversions are actually not all that usual, and not all these you get right. So everything's very clear and very clean what's going on the page. Of course, when you don't have conversions, you tend to do a lot of casting or conversions by hand, and that's messy. So we address that by changing constants pretty profoundly, and I'll talk about that in a little bit. You won't see 0x8 ULL in a Go program. The ULL is completely pointless. You can't even say it. Numbers are just numbers. And there's a strict separation between the interface and the implementation. That's part of keeping the concepts orthogonal and the type system clean. So there's a runtime, there's a garbage collection, there's good support for strings, maps, associative arrays, that kind of thing, and also the communication channels, which I'll talk about. And then there's really strong support for concurrency. It's actually some of the best concurrency stuff I think that's out there. It's really good. And then there's a package model, which I won't talk very much about because it's kind of takes a lot of explaining. But the notion here is that inside the packages, everything's explicit. What you depend on is explicit. The compiler rejects your program if you put in a dependency you don't need. It's all very clean. And so it makes tools easy to understand the dependencies, and it makes the builds guaranteed minimal. So that helps enormously. Regarding the dependencies, the linking can go faster, the compilation can go faster, but there's actually a notion in here that I think is important. The compiler actually pulls the transitive dependency information up the tree as it's compiling simply to reduce the number of files it has to look at, which in turn speeds up the compilation process. So if you have a program A.go that depends on B.go, that depends on C.go, which is a pretty standard kind of thing, in the usual way you have to compile them in reverse order because you've got to build the dependent stuff before the depending stuff. But the point is when you go to compile A.go, it doesn't need to compile C. It doesn't need to look at C.go at all. It doesn't even need to look at the object code for C because everything that B needs from C has already been pulled up into B.o. And that doesn't sound like a big deal, But when you're at scale, it's literally exponentially faster at building software when you get into these huge dependency trees. For concurrency, we sort of have a model. I'll touch on it today. There's a lot more stuff online about it. But we have a suggestion for how to write systems and servers as concurrent garbage collected processes, which we call Go routines, that have good support for the language and the runtime. We changed the name because they're slightly different from what you're used to. If you use words like thread or process or coroutine, it's not quite the same. So we have our own word, Go routine. The language takes care of managing the Go routines and managing the memory that they use and the communication between them. Stacks grow automatically. That's taken care of by the language, so you don't have to declare how big the stack's going to be. If it needs a bigger stack, it gets a bigger stack. If it needs a smaller stack, it uses less memory. And those stacks are the Go routines are then multiplexed onto threads. That's all done automatically for you and utterly transparently. And one of the reasons for needing garbage collection is that concurrent programming is very hard without garbage collection, because as you hand items around between these concurrent things, who owns the memory? Whose job is it to free it? And there's a lot of bookkeeping involved if the language or the system doesn't take care of that for you. So you need garbage collection to make concurrency work well. On the other hand, you need to get the garbage collection to work well, you need a language that makes garbage collection a feasible thing to do, which is another argument for doing a new language. So I don't have time to explain all of Go to you. It's a significant language. I'd say probably bigger than C, but not as big as C++. I don't have time to go through all of it, but I want to give you the flavor. So I'm going to go through about a dozen slides that are, I hope, sort of representative of the kinds of things that go on, but I'm going to leave out quite a bit. Lexically, it looks a little bit like C, actually a little more like C than this slide would let you believe. There's usually keywords involved introducing things. You see const and var. Const there means it's a constant, it's not the const keyword from C. It's a completely different meaning. It just means in the first line there, n is a constant 1024. And it's just a number. It's not an int, it's not a float, it's not an unsigned int, it's just a number. And there's a const string, and you can see we support Unicode just fine. In fact, the language requires that the input be UTF-8 encoded. And then you can declare variables with the var keyword in the usual way. You'll notice, I'm quite used to it now, but for C programmers, this looks backwards, because in C, you'd put the float before the x and the y. But they're reversed, and there's a long explanation on the web about why we did this. But the fundamental reason is it actually ends up being cleaner, because, for instance, in that declaration, x and y both have type float. Whereas if you flip it around, put the keyword first, things get a little funnier. And you can see what the C version of that would look like. You'd have to reproduce the star. So there's a simplification you get. There's characters, Unicode support, stuff like that. Then in this example, well, it's not really an example, just some lines of code. There's a type struct t that's defined. It's got a couple of fields within it that are both integers. Then we declare a variable t0, which is a new t. That should be pretty familiar what that means. But there's too much typing going on there. So the next line there, t1 colon equals new t, that's an old notation from some languages I've worked with before. What that colon equals means is declare and initialize. So those two lines are equivalent. Var t0 star t equals new t has too many t's in it. We can get rid of one of them by just having the type of t1 be derived from the expression that's used to declare it and initialize it. And you'll see that used a lot in Go code. The var doesn't show up nearly as much as the colon equals notation. There are control structures. They're actually quite interesting control structures, but just as a first blush, they're pretty much the same as C. They're actually quite a bit richer, but the basics are the same. The main difference is syntactic. The braces are required on the blocks, and there's no parentheses on, for instance, the conditional expression inside an if statement. That's just to clean up the grammar. So here's a real program. It's not hello world, it's echo this time, but it's got all the parts. The first line of the code says package main. That has some meaning in the language, although it may get muted. We're thinking about simplifying a few things, but at least for the moment, there's package main, and then you can see there's a function called main that's declared down below, and the program begins execution by starting main.main, initialization aside. There's a declaration of a flag from the flags package, so that makes -n turn off new lines from echo. It's not strictly a Unix echo because it's got real flag parsing, but it's essentially the same. Those import statements say we're going to use package OS, which does some stuff for us, and we're going to use the flag package, obviously. Now, the way the initialization stuff works is that n flag variable will be initialized before main starts executing. All the global variables get initialized and they can be initialized by arbitrary complex stuff before main starts. So then in main, we do a flag parse to get the command line pulled apart. And then we just loop over the arguments, which are now the property of the flag package, and it's the obvious loop accumulating. You can see plus equal on a string there to append to the string, and stuff like that. And then at the bottom, the flags are actually pointers in Go. The flag package makes them pointers. So if star end flag, which is a Boolean, is false, then you add a new line to the end of it. And then finally, you do a method call on os.studout to get the output up. So although pretty much every line of here is different from what you've seen before, it should be perfectly clear what's going on. I don't think you'll find that a mysterious program. So let's talk about constants. I said they're a little different. Constants in Go are what we like to think of as sort of typeless. They have no type, they have no size. They're just numbers. Or strings. You can have constants of strings and Booleans, but numbers are the interesting case. So in this little snippet here, it's just some constants being used. We start by defining a type tz for time zone, which is just an integer. And then we declare some constants, utc and est, and we declare them to have type tz and assign to those initial values. And you can pretty clear what's going on there. The parenthesis around the const is distributing the const declaration introducing keyword across the elements inside that declaration. So that's the same as saying two const declarations with the two variables in them. You'll see later on the next bit here that it actually matters that you can group them like this, because there's a thing called iota, which is an enumerating constant. It literally, for each const declaration, counts which element you're on. At every semicolon, it increments. Starts at 0, on the next line it's 1, the next line it's 2. And so here you can see we're declaring bit 0 and mask 0 to be uint 32s. And the first one is set to 1 shifted up iota. Iota starts out at 0 in every const. So that's 1 shifted up 0 and 1 shifted 0 minus 1. So that's a bit and a mask. And then the next line does it again, but now iota's gone up to 1, and so we get the next guy in the sequence. And you can see how to use that to build enumerated constants, but this is a slightly richer example. And again, to reduce typing, if you want, you can just say declaration, like the third line there, with a semicolon, and what that says is just keep doing what I did. Take the declaration initializer from the previous line and pretend I just typed that here. And so if you want to declare an enumerated constant, you can say const open parenthesis enum 0 equals iota, semicolon, and then just go enum 1, semicolon, enum 2, semicolon, and all the way down the page, and just have them declare sequential numbers for the constants. One of the important properties of these numeric constants in Go is that they're arbitrary precision. So here's a const, the logarithm of 2. You can see that's got, 40 or 50 decimal places in it, which is more than even a float 64 can represent. But that's a valid declaration is because they're just numbers. And then on the next line, we can actually compute log base 2 of e as 1 over log of 2. And that's a precise division because it's happening not in floating point space, but in arbitrary number precision space. So that's a very accurate reciprocal. And that kind of stuff is nice to do because you don't see casts and conversions and worries about overflows and underflows. Constants just take the job for you. And then we have values, obviously. There's an array-like type called a slice. There's arrays, but they're kind of peculiar. You don't use them much. Instead, you use a reference type called a slice. So weekend there is declared to be a slice of strings with Saturday and Sunday as strings declared inside it. And then we take the time zones and declare time zones map to be a map from string to TZ or time zone. And you can see how that works. It's pretty straightforward. There's a function declaration to do an add. You can see the function syntax there. There's actually a lot of interesting things on how functions deal with return values, which I'm not going to talk about today, but you should check that out. And then there's a declaration of a function type, which takes 2 integers and return int. So add is of type op. And then here we declare an RPC, which is a structure. I showed that before, but this is a slightly richer example. It's got A and B are integers. It's got an operator, and it's got a result, which is a pointer to an integer. And all of that should be fairly straightforward, even if the declarations look backwards to a C programmer. And then the last line there, we declare, using a structure literal, an instance of an RPC. And again, it's very simple. You just say type name, open brace, list the elements of the structure, closing brace, and now you've got a value. You can assign that to, or in this case, initialize a new variable to that value. So I said it's an object-oriented language. We haven't seen much yet. There was actually one in the, there was a method in the in the echo example where we wrote to os.stdout, but let's talk about methods because they're kind of different. So here's a type called point that has x and y. Now, those are uppercase. And the reason is, in Go, the complete decision about whether an identifier is visible outside the package or not is whether or not it starts with an uppercase Unicode letter. That's it. So if a variable is, or a type or whatever declared at the top level is uppercase, it's visible to clients of the package. If it's lowercase, it's not. Inside a global struct, if a method or a field is uppercase, it's visible to clients of the package. Otherwise, it's not. That's it. It's really simple. So there's that type. Now we're going to define a couple of methods on it. And the declaration syntax for a method, you'll notice it's not declared inside the struct. And the reason, we'll see in a minute, is that methods and structs are independent ideas. You can have methods on things other than structs. So it wouldn't make sense to just put them inside the struct declaration. What you do is you say, here's a func, and then before the name of the method, you write in parentheses, kind of like its own little one-element parameter list, receiver declaration. And the receiver is a shorthand for the thing that's receiving the method when it's called. So this says that scale is a method of type star point, and it takes a float argument, and then the implementation is inside, and it just multiplies up the point by the scale factor. You'll notice that the receiver is explicit. There's no this automatic or anything like that. You have to actually say declare receiver and use it if you need to access the fields of the struct inside the method. And then there's abs. You can imagine what that is. There's a square root, which is a function inside the math package computing the hypotenuse of the pointer, the absolute magnitude of the vector. And then here's we declare an x. Now this time you notice there's an ampersand before the point word there. Point of 3,4 is a value. Ampersand point of 3,4 allocates. It's like a constructor-like thing to create a pointer to a new instance of that. And that every time you execute that, you get a new instance of point that initializes to 3,4. Then you can call x.scale, which is just what you'd expect to be able to do. Okay, so that's pretty simple. The syntax is slightly different, but the ideas are pretty simple. Now, it gets more interesting because you can put methods on any type you define. And here's a full example. This is another complete program that actually does something a little different. So again, we start with package main, and now we import funct, which is the formatted printing package. It has printf and stuff like that in it. And then here's our type tzint coming back. And now we declare a few more of these constants. We have an hour, which is of type tz, which is 60 minutes times 60 seconds. And then we declare, just to make it short, 2 time zones, 0 hours and -5 hours for UTC and EST. Okay? Then we declare a map from the names to the values of those time zones. That should be familiar in the time zones. We actually had that essentially same example before. And now we put a method on a time zone. Now time zone is just an int, but I'm going to put a method on it. So I declare a function called capital string that returns a string. Its receiver is tz, lowercase, but it's of type tz, uppercase. Notice it's not a pointer. It's really important. It doesn't have to be a pointer. And then, using a variant of the for loop that lets you range over the elements of a collection, I say name, zone is range of time zones. What I'm looking for is the element of the time zone map whose value is equal to the value of tz, and that's the name of the guy I want. So it's like reversing the map. So I just loop over all the elements looking for the one whose time zone is equal to the zone of that element of the map, and if that's true, I return the name. And you can see there's actually quite a bit going on in there. There's the range, which is giving you the iterator. There's a colon equals to declare loop variables that work over the elements of the thing inside, and all on. But of course, you might get a value of tz integer that's not an exact time zone number. And so if that happens, we finish the loop and we return funct.sprintf of blah, blah, blah. And sprintf is analogous to the standard C sprintf, but actually returns a new string. It doesn't put into a buffer. So that's an implementation of a method that lets you print time zones in interesting ways. So we can use it in our main function by saying, if we just say funct.println of est, println is a variant of print that doesn't require a format, it'll work. It'll actually print out est by catching it in the inner loop of the string method. And notice that println est knows under the covers by mechanisms that are described at length on the website how that the time zone type has a string method, and that's how you should pretty print it if you get a value of that type. So that's all you need to do to make it print itself. And then as another example, we can print println 5 times hour over 2, and it comes out as +2:30 because the printf at the bottom works. So this is a fairly contrived example, but you can see there's a fair bit going on here. Having methods on general types is, as any Smalltalk programmer will know, a very convenient thing to do. But by separating them methods away from structs or classes, we actually introduce some new ideas that you can play with. And that's pretty fun. Okay. So now we come to something that I will not be able to describe in full in the time available, but they're pretty interesting, and they're arguably the most novel thing about Go, and that is the concept of an interface. An interface is what's the word? A formalization of the concept of a set of methods. So we can declare a method, an interface type, magnitude, and say that anything that implements the magnitude interface is something that implements the abs method that returns a float. And of course, there could be lots of other things in there, but we'll assume for the moment there's just one. So remember, we declared an abs method for the type star point. So we had an x from the previous slide. Do it back there, that x address of 0.34, that's the same x. We can use it here. We can declare a variable with the interface type magnitude and assign to it the value x. And the reason we can do that is x is an implementation of that interface. And so that's a valid assignment. Okay? And having done that, had I typed var mag magnitude instead of m magnitude, oh no, I got it right, sorry, confusing myself. Var m magnitude is a variable, we assign it to x, and then we declare a new variable mag that's m.ab, so it's just the vector length of the point x. But now we declare another type, point 3, which has 3 coordinates. Define the abs method for that, same idea, and now we can assign m equal to a point 3, and that value still is an interface value, but inside it is an object that has the implementation of the abs method. And so we can call the abs method on that and add that to the variable that we've got. And then we can do it again. And this time, just to be fun, we'll declare a polar object, which is r and theta, and of course that's a capital theta because it's a public field. And then we declare p polar. Notice it's not a pointer this time. Why make it a pointer? It doesn't matter. So we just make it a value polar, and it returns the radius of the thing, which is the definition of the magnitude. And then we assign a value of that type to m, and now we can add another thing into the magnitude. So the interface variable is letting you define, I can work with anything that implements these methods, and anything at all will do. Here I use 3 different representations of a coordinate, but they're quite different in character. Under the covers, it's all very simple. And the key point is that nowhere does point, 0.3, or polar have to tell you that it implements the magnitude interface. It implements it de facto because it satisfies the methods that are defined by the interface. And there's way more going on there than I have time to talk about. But I have to talk about one very important concept behind them, which is the generality that they give you. Because any method it can be part of an interface, and an interface can be any method, it's all it's not one-to-one, it's many-to-many, it's all mixed up. And so a struct of a given type may implement multiple interfaces depending on what interfaces you're using. And that gives you the opportunity to define very simple interfaces that define very general properties. And a really good example of this is in the I/O package, and it's called the writer interface. And a writer is anything that implements a standard write call, and that's what we define a standard write call to be. You notice there's a slice of bytes that is the data you're going to write. It has a length implicitly inside it, so we don't need a byte count. And it returns, here's that function declaration I was hinting at before, returns a pair, a count, and an error. But don't worry about that. Just think about the writer. The writer says anything that implements this standard form of the write call can be used to write to. Makes sense. It's almost a tautology. But now, anything you implement write for can be used by anybody that only needs something that implements write. Doesn't matter what other properties it has. So, for instance, fump.printf, which is just what it sounds, fump.fprintf, pardon me, which is pretty much what it sounds like, doesn't take a file as the first argument. It takes an io.writer as its first argument. And as a result, you can call fump.fprintf on a network connection, a pipe, a file descriptor, a buffer, all kinds of other things. Anything that implements write, a cryptography pipeline. And then the way buffered I/O is done in Go is that there is no such thing as buffered I/O. There's just buffering. And what happens is, if you want to create a buffered version of something, you give it a writer, which is anything that implements write under the covers, and it gives you back a buffered version of that same thing that you can use where you used before. So here's an example that puts that together. Again, a complete program starting with package main. We import buff.io, funct, and os again. And now we wrote to os.studout before, but now we're going to use fprintf to write to it to make it explicit. So we say funct.fprintf os.studout hello. Then we call buff.io.newWriter. We pass it os.studout, but newWriter, all it cares about os.studout is that it implements the write call. And the newWriter function inside buff.io returns something else that implements the writer interface. And so I can write to it. So I can call funct.fprintf of buff. And now I have a buffered write, so I better flush it when I'm done. But you see that the fprintf used two different types in there for its output, and it worked because it underneath, if you look at the fprintf declaration, all it cares about is that the thing that is being passed in implements the write call, which of course they do. And it's type check, so you know they do. So there's a lot more of that stuff to talk about too, but we're trying to skip through the highlights. Communication channels are a little less radical than interfaces because they're based on work done in some earlier languages going back to Hoare's CSP. But unlike Hoare's original CSP, the communication is done through first-class values called channels. His second round of it, done about 10 years later, had these, but we played with them linguistically by then. And the idea is you make a channel that has type string. That means you can send and receive strings on that channel. It's just like a pipe that you can send typed values through. And so that notation with the left-facing arrow is the communication operator. When used infix, it means send. So that sends the string hello down the channel. And somewhere else, some other time, some other Go routine can do read from channel C by doing a prefix operator on C of that communications and get out the greeting. So it'll see greeting is assigned to hello. And these have to be done in different Go routines because the channels are synchronous by default, although you can control that when you allocate them. And one of the cool things about having them is you can make them, channels can actually be first-class values, which means you can pass a channel on a channel. And I'll show you in a minute that actually gives you some interesting capability. So if you have someone else wants to have this channel that you can send greetings on, you can pass it to him over a channel, and then he can send you greetings, right? So to do that, though, we have to talk a little bit about Go routines. So imagine you have some calculation that just takes far too long, right? Who wants to wait around for that? You're going to block forever waiting for the calculation, but maybe you don't want to. What you can do instead is create a channel to get the answer back on, and then declare a function, wrapper, that takes the value, the parameter for the calculation, and a channel, invokes the calculation, and then when it's done, sends the result back. And I broke it into 2 lines just to make it easier to read. You'd probably just write C gets long calculation of A in the real code, okay? And then to run the thing, there's a go keyword. Go is a keyword. Go wrapper of 17C says, take the function call 17, C and run in the background, let me keep going. Okay? And then eventually, you want to hear what happened. So once you're finished doing your business, you come back and say, okay, I'm ready for the answer now. And you say, now I want to receive from C and get the result. So I've taken this calculation and I've fobbed it off over here, and then it flows back to me by doing the receive on the channel down underneath. That should be fairly easy to follow. This might not be so easy, but we'll try. This is a multiplex server, at least the server side of it. I'll show you the client on the next slide. And the idea here, remember I said you can pass a channel to a channel. What we have is a request, which is a request for the server to implement. That's trivial. It just takes a pair of integers and a channel in which to reply. It's very much like we did before on the previous slide, except generalized somewhat. We define a binary operator type, and we define a function run that takes a binary operator and a request and sends on the reply channel inside the request the value of running the operator on the arguments inside the request. So that's just turning the operation and the sending of the thing from the previous slide into a function. Not very exciting yet. But then we define a server function that takes an operator that it's going to serve and a channel of requests. And it just sits in a loop, reading requests from the service channel, and then saying run of op request, but it puts a go keyword at the beginning. So it runs all these requests in parallel in the background. The server's never blocked. It's always ready to receive another call, no matter how much is going on. Obviously, there's issues about rate limiting and stuff like that, but let's not worry about those. The key point is that that's basically a server loop. And then, to make it easy to use for the client, we define a public function or an exported function by starting with a capital letter, start server. And it says, take an operator and start a server for that operator and return the channel on which those requests can be sent. So what we do is we allocate a channel of star request. We start the server process, which in turn is going to start the little implementers of the operator as they come in. And then we return the channel as the return value from start server. So you call a function, you get a channel back. Now you've got a thing you can talk to. And that is sort of fundamental idiom about how you use this stuff to build services. Okay? So on the client side, it looks like this. You say server is start server of, here's a function. Now notice I'm just writing a function in line there. Go has full closure, so you just write them down as expressions. And so now I've got a server running that's going to add numbers for me, and I've got a channel to that server in the variable called lowercase server. I allocate a couple of requests in the obvious way, and inside the request, I allocate new channels because I want them to respond to me on separate channels for whatever reason. Okay? And then I can send the request to the server. It doesn't matter what order I send them. It's totally non-blocking. I can send them any order I want. And then I can print them out again, print the results as they come back, and I don't have to worry about the ordering because, again, it's totally parallel. So in fact, I send 1 first but ask for 2 first. And if 2 takes forever, I'll still hang around there waiting for the response to come back. And once it finally does, then I'll print the value on 1, even if 1 is ready sooner. So this is very rushed through here, so I apologize if I left you a little befuddled. But there's examples like this in the tutorial and some other documents that should make it a little clearer what's going on if that loses you. Now, if we go back to the server here, remember I said it has a rate limiting issue. It also has the problem that it runs forever. You want to be able to shut it down. One way to do that is to use a control structure in Go called a select, which is quite a rich control structure. But the basic idea is given a set of communications on channels, select lets you essentially wait for any one of them to become ready. And once it does become ready, let that single thing communicate. So it's like a switch statement for communication. So if we replace the inner loop of server, which was just, remember, get a request and then run Go on it, with an operator that has a select statement inside it and a second channel called quit that's passed into the server when we create it, then we can just run this normally and it'll just do what it was doing before. But as soon as you want it to go away, we just send a signal by sending a Boolean of any value, it doesn't matter what, on the quit channel, and that branch of the select will fire and this function will return, which is equivalent to exiting the Go routine. So that's, again, pretty quick, and I apologize for that, but I wanted to make sure we hit some of those points. And in fact, there is a lot more to talk about. I haven't talked much about package construction. Initialization is actually quite interesting in Go. It's sort of hard to see, but it does a lot for you. It can help you set up things like RPC servers with almost no code and stuff like that. There's full reflection. You can reflect on data, you can reflect on functions, channels, maps, all that kind of stuff. It's got some interesting dynamic typing going on if you wanted to, but you don't have to use it. There's a thing called embedding that is a little bit like inheritance, but somewhat more simple and yet general. There's iterators that come out of the way the range thing works on 4s and how channels function, things like that. And there's some interesting testing software. But I don't have time to talk about any of these right here, but I just want to make it clear there's a lot more to the language than what I've had time to show you. So let me close this section with another interesting example. This is a real communications example. Remember we started this language because we want to build servers. And one of the problems with building servers in the modern world is there's this model of a thread per request, which is quite labor intensive and resource intensive to run and quite difficult to get right in modern languages. And we wanted to make it easy to think about having tens of thousands or even hundreds of thousands of threads, whatever they are, working on your behalf. And to prove that we've got some way towards that, this is an example that will create 100,000 Go routines and then make them do something. And what it does, you probably won't be able to decode this in real time, but what it does is it has a little function f there that all it does is read a value from a channel, add 1 to it, and send it out again. So there, left gets 1 plus get from right is that thing inside f. And it just passes this token along but adds 1 to it, okay? And inside main, we declare the leftmost piece, I'll go your direction, and then a couple of variables. And then for the number of Go routines you want to start, we sort of thread a new piece on and walk away along. But we remember where we started. So we stitch together a bunch of Go routines like this, each of which is passing a channel value along to the next one, until you end up constructing, in this case, 100,000 Go routines all strung together like pearls on a string. and each of them is waiting for the guy upstream to give them a value. So then right at the bottom there, after the loop, once we've built this thing, we say drop a value into the right-hand side, and it goes and pops out the left. And the value that comes out is, of course, the number of go routines in the chain because we've added one for each step. Okay? So you can examine that later if it confuses you, but let me show it to you actually running. Okay. So, oh dear. I have to remove the wrong file. Okay, sorry it took so long. And now I'll run it. Now remember, this is just a little Mac Air. It's not even very fast. That's 100,000 threads of control. I won't say threads because that's not how it's done. But just in case you're wondering, it takes about 1.5 seconds to manage 100,000 Go routines. And it's real, it's honest to God management too. It's creating them, it's stitching them together with communication, it's doing the communication, and it's tearing them down. This doesn't create them all and then send kill. This is a legal, honest build, use them, tear them down. It's kind of the minimum thing you can do that. But still, 100,000 is an interesting number. And we could go more, but it starts to use up memory. So that's just proof that there's, I didn't want to do that. There we go. So that's concurrency, showing that you can at least conceptually have many, many things. Now the Go routine implementation has to worry about real threading and real stuff like that when you're doing I/O operations that could block, but that is taken care of. So even though that's a simple mind example, it's indicative of something that really works. So let me talk a little bit about the status. There's actually quite a bit to say. We have two complete implementations in two different compiler technologies. Ken Thompson wrote a suite loosely based on some of the Plan 9 tools, but it's from scratch. And using the peculiar notation, 6G is the AMD, it's a 64-bit x86 compiler. There's also a 386 one and an ARM, which is 5 for reasons you don't even need to ask. But anyway, the point is there is a compiler. That's the one I've been using today. It's somewhat more experimental than the other compiler, but as you've seen, it generates code quickly. The code that generates is pretty good. It's not as good as what comes out of GCC, but it's better than you might think for a compiler that goes that fast. But in order to do that, it's got its own rules, and so the output is not linkable directly with GCC. But there is a foreign function interface support that's coming along pretty well. We can call C code from Go with this compiler just fine, and once we get Swig working, we'll be able to call C++ code. And then Ian Taylor wrote a GCC front end for Go, which is a completely different implementation. I should say, by the way, that Ken's compiler is written in C for bootstrapping reasons, although honestly it would be a great language to write a compiler in, but it's written in C for now. And Ian Taylor's thing is a C++ front end for the GCC backend. It generates excellent code, it's GCC quality. But it's not as fast. It's about something like 4 or 5 times slower. But the real advantage of compiling Go isn't the compiler speed, it's the compilation speed. The whole picture is where the speed really comes from. And both these compilers support 32 and 64-bit x86, and we have an ARM compiler that Kai has been working on that's almost ready. I think it's up to 97% to test suite compliance now, so yeah, we're very close. We hope to have it ready in time for the open source release. And the performance of the generated code, it varies obviously because it's different. But if you avoid some of the libraries for which we have weak implementations, typical inner loop kind of performance or standard programming gets you typically in the 10 to 20% range, with GCC tending to be more like, by which I mean 10% slower than C. And then Ken's compiler is typically like 20% slower than C. So 1.1x to 1.2x. But this is for a type safe, statically compiled, garbage collected language. It's pretty nice. And I'm happy to give up 10%. That's even with Moore's law slowing down, that's still not very much clock time on the calendar. So there's a runtime. It handles all the memory allocation, garbage collection, stuff like that. The stack handling stuff, which is pretty special but very important. The Go routine support, channel, slices, maps, reflection, all that stuff is built into a real runtime. So even though it's a systems language, it has a really powerful runtime system, including dynamic type reflection. And it's pretty solid. It's improving. It's got ways to go, especially in the memory allocation and some of the scheduling stuff. But that's yet to come, but we're working on it. 6G has, I think, very good Go routine support, and much of them onto threads well. and implements what we call segmented stacks, which is how we keep the footprint small but let them grow as they need to. GCC Go is a little behind on that because Ian's been working on a few other things lately. But we hope by the end of the year to have all of that stuff working in GCC Go, and they'll basically be at the same stage at that point. But even so, GCC Go can compile all the code and run it now. The garbage collector, 6G has a simple but effective mark and sweep collector, emphasis on simple. But work is underway to do a much better job. We believe with multi-core machines, you can actually do concurrent garbage collection with essentially zero latency and very little constant overhead. And IBM has this garbage collector technology that we think is pretty exciting, but we think building on that stuff, we can actually make our real goals, which are to avoid a lot of the pitfalls that garbage collectors tend to have. And we've done work in other languages before that indicate this really can be done. And now that we have multi-core machines, we believe we can really solve it. GCC Go at the moment has no collector, but as I said, we're working on a common runtime, and I hope by the time this collector is done, it's designed to run with either compiler. It's part of the general runtime. So both compilers will have real garbage collectors inside them. There's lots of libraries. There's tons more to do, but we have a pretty good start. We've got obviously OS and I/O stuff. I showed you some of that. It's got a nice simple math package. It's got strings, good support for Unicode, rudimentary but functional regular expression implementation. It's got runtime reflection, command line flags, and logging, which are very nice to use. It's got full hashes and crypto and all that kind of stuff. It's got a really good testing tool and the libraries to support it. Standard networking libraries, just like you'd expect, including a native RPC implementation that's kind of pretty. There's a really interesting template library based on some work that Andy Chu did that lets you write HTML or in fact anything at all using this to generate really simple data-driven page generation. It's really quite nice. Andy gets most of the credit for that. And there's lots more, but you can see there's actually quite a bit in place already. So one of the most interesting programs written in Go is a pair of things that are related. They share a lot of code called GoDoc and GoFumt. GoDoc is analogous to JavaDoc. It serves documents to requests to look up, what this package does or what that function does. And there's a set of links listed there. Golang.org is the top level guy. That's running GoDoc. It serves the landing page. And underneath that, you can find all the other documents, the specification, the tutorials, and FAQs and stuff like that. But if you dig down into the package subdirectory, that's really interesting, automatically generated package documentation. It's actually quite rich. And then under the source directory is all the source code served, but of course you can get that out of this code repository too. The difference is that the source is processed by the code in GoFumt. And GoFumt is a pretty printer, and all of the code in the repository has been formatted by GoFumt. So rather than set a bunch of style rules, we have a program that says this is what code looks like. And you just run it through GoFumt when you check it in. And that just settles all those arguments. And if you want to debate, if you want to debate, we got to debate by changing GoFumt. You can't debate by changing a document. And I think it does an amazingly good job. Actually, Robert Griesman wrote that and did a really good job with it. We have a debugger. It's not quite ready, but it's pretty close. I hope by the end of the year we'll have something functional that we would be happy to show. But it's coming along. And it will work with either environment, but at the moment it's working in the 6G world primarily. GCC Go users can, of course, use GDB. GDB doesn't understand the symbol tables that are coming out of Ken's compiler, so it doesn't work very well with that. But with GCC Go compilation, you can use GDB, but it thinks it's a C program, it's debugging, and there's some weirdness in the symbol table. And also doesn't know anything about the runtime, which is a critical thing when you're debugging an environment like this. So we really got to get our debugger up to scratch. We had a summer intern, Austin Clement, was here working on that, and it's pretty close, but not quite ready for real use. One question everybody wants to know is, what about generics? And the answer is Go doesn't have them yet. We don't understand exactly what they do in Go's world. They're quite subtle. The easy examples are easy to write down. It's obvious what the easy examples do, but the complete correct definition is going to be quite complicated. We want to make sure we get it right. In some ways, Go makes it simpler because there's no type inheritance, and that eliminates one branch of complexity in generics. But on the other hand, you can put methods on things that are values of arbitrary size. And so that's a consequence in the other direction. So it complicates and simplifies at the same time. And we just don't think we understand it well enough to do them yet. Also, in the current world, although generics would definitely be useful and to solve a lot of problems, the map and slice implementations and the interfaces themselves actually cover a lot of the sort of obvious examples for generics, which is not to say they wouldn't cover a lot of others if they came along, but the need isn't quite as acute as it is in a language that doesn't have those features. And you can, in fact, build collections fairly nicely using what's called the empty interface, which is just interface open and close. That's an interface that implements no methods, because everything in the world satisfies the empty interface. It's kind of a little bit like, but in a completely different meaning, the object in Java. And you can build collections that use that, and there's quite a few checked in. But they have the disadvantage that they're not type safe in the sense you have to unbox manually and stuff like that. They're not really what we would propose to do instead. It's just what we're using for now while we struggle with this question. So generics, not yet, but they're very subtle. It's interesting, in the Coders at Work book, Josh Block has a long discussion about them. And I think most people think that Java generics work really well, including Josh, but he points out they're actually quite a bit harder to get right than you think. And maybe it's time to think really hard before you put them in. So they may come, but they're not there now. And of course, there's a million other things. Where's my feature? Everybody who programs has a feature they want, and chances are that some of the things you really think are important are missing. Or they might be there, but not in the way you're used to. A really good example is enum. There's no enum, but there is iota. And iota is an interesting thing, but it's not an enum. It's different. So it may not be there, but there may be some way to do what you want that's just as good or different or almost as good or maybe even better. But why isn't your feature there? Well, maybe it doesn't really work in the language. Like there's no pointer arithmetic. Pointer arithmetic is nice, but we can't do pointer arithmetic and make the language safe. It's just not there. And the compiler makes up for it by trying to compile away some of the inefficiencies you get by having to do indexing everywhere. But on the other hand, you get a safe language. So a lot of the things that people expect in languages like this are not there because they break the rules. We won't have them. Or at least they break our principles about what we think the language should do. And there's also possible, like generics is a good example. They're just not at the top of our list. It doesn't mean they won't happen. Union types is another one we've been thinking about. Actually, have, I think, a pretty good proposal for them, but we haven't done that yet. So it's possible some of the things you're pining for will actually occur fairly soon or not too far out. But it's a different enough language that even if it doesn't have the features you want, it may have features you haven't used before. In fact, I guarantee it has some you haven't used before. The interface stuff is very interesting. And don't let the lack of things you expect stop you from playing with the things that are there and seeing that it does actually do some pretty interesting stuff. And there's a lot more information on this topic available. There's actually an explicit language design FAQ on the website, and it talks about a lot of the why things aren't there things. So to conclude, I think we have a really nice language. I'm having more fun programming than I've had in a long time because I feel like I'm getting work done, because I am getting work done. It's early yet. I think the language is going to evolve some more. There's things we know, but a lot of the basics are locked down pretty well. I think we're pretty comfortable with them. It's a very comfortable language to work in. It's very productive. You can write code really fast and have it work and be safe. There's tons of documentation. There's a specification, the complete spec of the language. There's a simple tutorial for beginners. There's a document called Effective Go, which is growing to sort of explain idioms and how you think about things in the language differently. There's some FAQs, and there's even other things than that. All the implementations are available as open source, the 6G, 8G, 5G suite, and all of its tools. The GCC and all that stuff is also in a different place, but it's also going out. It'll be linked from the landing page. And so if you want to try it, go get it. If you want to help, please do. There's tons of work to do to build it up to another level. We really are welcoming people to come in and talk to us about stuff, especially if they want to help us do some interesting library work or build new tools. There's plenty of room for things to happen. So that's our site, and that's our language. Thanks for listening.